Alright, today's class we're going to look at two brand new reactions. The first one's going to be the Wittig reaction, and I want to show you guys the overall reaction first, and then we'll talk about the mechanism. This reaction works with ketones or aldehydes. I'm just going to show a generic ketone for the example, but we'll make a note that this can be an aldehyde or a ketone. And then what we're going to do is we're going to treat it with this strange looking reagent. This is let me clean this up, PH3P, so triphenylphosphine, that is covalently bound to another carbon. And this carbon will have an R group coming off of it, and oftentimes another hydrogen. The carbon in this example has a lone pair and a negative charge, and the phosphorus has a positive charge. This is called an ylide. And this is a really excellent way of forming new carbon-carbon bonds, right? Because if we look at the carbon here, the carbon's got a negative charge. It's a good nucleophile. We know carbons with negative charges like to add into ketones and aldehydes.
So this is the second reactant that we can use to form the carbon-carbon bond instead of the Grignard?
Yeah. This is similar to a Grignard in that it's a carbon-based nucleophile. However, we'll see the bond we make is a little bit different than with the Grignard reaction.
Okay.
The bond that we make actually has an alkene. So in a Grignard reaction, we can use it to make carbon-carbon single bonds. A Wittig reaction is used to form carbon-carbon double bonds. One thing I did want to point out is that the alkene that is formed is normally the Z alkene. We're not going to really get into the reasons behind that, but you can use special conditions to favor either E or Z alkenes with a Wittig reaction. So the first thing we have to do anytime we're dealing with a Wittig reaction is show formation of our ylide. So let's go through that mechanism. First thing we've got to do is get some triphenylphosphine. This is a reagent you can buy from most chemical suppliers. And then the next thing you've got to do is get an alkyl halide. So in this alkyl halide example, I'm just going to draw it as a generic X. And we've got this R group here. In fact, let me keep the R group blue, similar to our top example. What do you think could happen when we mix these two? Think first term. Yeah, it's SN2 substitution, right? We've got a nucleophile, we've got an electrophile with a leaving group on it. So in this example, we'll do a backside attack, kick off our leaving group. And because this is an SN2 attack, we know that this works with methyl or primary alkyl halides the best. Why doesn't it work very well with secondary, and why won't it work at all with the tertiary alkyl halide? Sterics, right? We've got to attack from the backside. The more crowded that backside is, the less likely this reaction will be. All right, so let's draw our product that we get out. So we've got this new bond, and we've got this R group here. This phosphorus now has a positive charge. And we've kicked off this alkyl halide leaving group. The next step, we have to treat it with a really strong base. Typically the base that we use is butyl lithium. Oops. This is kind of a pain to draw out all the time, so normally chemists will abbreviate this as butyl lithium. And in this next step, this butyl lithium will come grab one of these protons and clamp down. So now we've got a phosphorus double bond to a carbon, we've got our H, and we've got our R group. This is what's known as a phosphorene, so let's make a little note. It's not quite our ylide, but in this case we can actually think about this being in resonance, where we can take this pi bond, dump it over to the carbon, and give that carbon a formal negative charge. And there we go. We've got our reagent. Oop, I forgot my positive charge. And this makes the carbon incredibly nucleophilic. Oftentimes people, instead of calling it an ylide, because that sounds kind of weird, they'll just call it the Wittig reagent, like a Grignard reagent. All right, let's take a look at the next step in this reaction. It's a good question. I've asked myself that. Normally you hear it just called an ylide, but the phosphorenes when you have the true double bond representation. So let's do the overall mechanism now. And for this mechanism, I'm just going to choose acetone. This is a simple example. And I'm going to use a generic ylide with an R group on it. Actually, let me even label the carbon here. This carbon's got a negative charge. It's single bonded to our phosphorus with 3 phenyl groups. We know the phosphorus has a positive charge. Let me draw that carbon a little bit bigger. There we go. So the carbon we know is a good nucleophile because it's got a negative charge. It's going to add into our ketone and kick up electrons. So let's try to figure out what this intermediate must look like. This oxygen now has a formal negative charge. We've got 2 methyl groups coming off of it. We've got this carbon with a hydrogen and an R group that formed that covalent bond. And then up here we've got phosphorus with 3 phenyl groups dangling off of it. Oops. And this phosphorus has a positive charge. You might notice that phosphorus doesn't follow the octet rule in the way we're traditionally taught as organic chemists. So what do you think could happen in the next step? Yeah, it's just going to form a ring. Got opposite charges right next to each other. When we do this, we now get a 4-membered ring. With 3 phosphorus groups coming off. And we've got these 2 methyl groups coming off in this position. All right, the intermediate in the top right-hand corner is called a beta-ene. And then the more important intermediate is the one shown in the bottom right-hand corner, that 4-membered ring. This is called an oxaphosphatane. It's a mouthful. This is a pretty high energy intermediate. What will happen next is that this set of electrons will actually dump over and form a new pi bond between oxygen and phosphorus. And then this bond will clamp down and form a new pi bond between two carbons.
Is there any reason behind it?
Yeah, we'll get to that in 1 second here. So let's draw our intermediate now. Or actually our final product. So on one side we formed our new alkene that we know is normally going to be a Z alkene. And then on the other side, we form triphenylphosphine oxide. Triphenylphosphine oxide is this huge thermodynamic driving force. Once you make it, you've essentially driven the reaction to completion. It's very, very stable. It doesn't want to do anything else after that. So let's even make a little note of that. It's a thermodynamic driving force. So it's a pretty handy reaction for forming carbon-carbon double bonds. A really nice way of thinking about this reaction is it's essentially the reverse of ozonolysis, right? With ozonolysis, we could take this, cleave it apart, and get back our acetone, right? So in this case, we're just taking that idea of ozonolysis, but forcing it to go in the reverse direction. And we can actually functionalize molecules quite a bit using this technique. It's a very, very useful mechanism.
Are the three rings ever strictly new at all? Ever?
The what rings?
The three pHs, are they ever needed?
Yeah, I mean, phosphorus does weird chemistry, and I think we'll kind of leave it at that. As organic chemists, I really like to focus on that, the second row elements. Once we get into like third, fourth row, things start behaving pretty strangely. So phosphorus is actually okay having those phenyl rings, even though it is what appears to be really sterically crowded.
So, is it just weird chemistry that makes that so thermodynamically favorable?
Yeah.
Okay.
Yeah, phosphorus is a pretty unique compound, and we used to call it brick dust. It's actually a pain in the butt to remove from a reaction because oftentimes you have to run 2 or 3 columns to get rid of all of the triphenylphosphine oxide. You can imagine even a little bit, you've got that aromatic peak that shows up in your NMR and you're like, dang it, I have to run another column to get rid of more triphenylphosphine oxide. All right, let's do a little bit of a practice problem here. How to pick a route. All right, so let's say I want to make this compound. This is a practice problem I actually pulled from the Klein textbook. And the double bond is right there. Anytime you see a double bond like this, you could say, well, we could make this using a Wittig reaction, right? So let's kind of ask ourselves, how can we make this? Okay, so let's kind of break this apart into 2 possible options. The first option is let's have everything on the left be your ketone or aldehyde, and everything on the right be your ylide. So kind of like with ozonolysis, we can clip this in half, right? So if the left-hand side is going to be our ketone or aldehyde, Do you think it's going to be the ketone or the aldehyde? That was kind of a weird way to phrase that question, but an aldehyde, right? Because we've also got this hydrogen sticking off right here. So one option is we use the left-hand side as our ketone or aldehyde starting material. The other option is, well, what if we use the right-hand side? Right? Let's figure out which ylid we would have to use for each of these examples. We know each of them has a triphenylphosphine. This phosphorus has a positive charge. And then all of the unaccounted for carbons must be coming off of the phosphorus, right? So if we look at the one on the right, or sorry, the left, that means essentially this must be our ylid, right? So any unaccounted for carbons that aren't a part of your ketone or aldehyde must have been bonded to that phosphorus. If we think about the one on the right, we can do the same thing. So I want you guys to figure out what the ylid would be for the one on the right.
Where's the negative charge on that one?
It's on the carbon. You see how that inner carbon, I'll even label it green right there. That carbon has a lone pair on it, giving it a formal negative charge. So the question is, what's dangling off here? I'm going to actually extend this out. Raise your hand if you think you got it already. A few people? Okay. I'll give you guys a hint here. Let's label everything using different colors. So in this one, we said that everything coming off the left side, we can label that as blue, and then we add in that oxygen, right? That means that everything coming off of here must have been coming off of our ylid. But on this one, we're saying, all right, everything in green is our ketone, which means our ylid must be everything that's in blue, right? So let's plug that in. And let me trace over it with blue. Yep.
Is the negative charge always next to the positive charge on the phosphorus?
Yes. It's always going to be a phosphorus with a positive charge right next to a carbon with a negative charge. And that's because of the resonance form that I drew above. You can sometimes draw that as a double bond.
So can we think about a way that we just kind of get rid of the phosphorus and the hydrogen, and then we just stick the rest of them into the oxygen position?
Not quite. I mean, I want you guys to know the overall mechanism, and I want you to know how to do retrosynthetic analysis with the Wittig reaction. One question I do have for you guys, though, more abstractly, is which route would you prefer? The left one or the right one? And why?
Right one.
I heard some people say the right one. Does anybody want to offer an explanation?
Because it looks simple.
It looks simple. Does anybody, Sarah?
The negative charge is benzoic.
It's not benzoic because it's on a cyclohexane.
It's not a benzoic.
Seems more accessible. Does anybody have another reason? Well, let's go back and let's try to ask ourselves, all right, how can we make this ylid, right?
The long pair electrons is not in the back.
If we think about it, let's even scroll up. Up here I said if we want to make our ylid formation really works well if you've got a methyl alkyl halide or a primary alkyl halide.
Because that's tertiary is not favorable.
Yeah, if we think about this one down here, it's secondary. So this one would require a secondary alkyl halide. This one over here would require a primary alkyl halide. We just said that when we're trying to form an ylid, we generally prefer methyl or primary. That means that this route is going to be preferred over the other route. So let's even make just a little note there. So that's the other thing you have to consider anytime you're doing a retrosynthesis problem that involves a Wittig reaction. Does that make sense? You guys want to see the whole forward mechanism with this? All right, let's do the full forward mechanism. And I want you to start from the alkyl halide. So I'll give you guys a minute to do the full forward mechanism on that reaction. Figure out what alkyl halide you need, and then every reagent from there on out in order to get to our final product. I can zoom out. There we go. You guys getting pretty close? All right, I'll give you guys another minute. Then I'll give you guys a practice problem from an old exam. All right, let's try to do this as a class now. We know we need an alkyl halide. So in this case, we can use, I don't know, we'll just pick some leaving group like bromine. And then what are we going to react this with for step one? To make our ylid? Yeah, triphenylphosphine. So PPH3. This has a lone pair. We know this will go around, do a backside attack. We've got both of these dangling off. And now in order to form our ylid, what's our next reagent going to be? Yeah, butyl lithium. So let's do Bu minus Li plus. And this will come grab this proton, dump electrons down. We've now got a negative charge there. The next step, now that we've got our ylid, we can add in our aldehyde or our ketone. In this case, we said we wanted to use the ketone. So this negative charge can add in, kick up electrons. Oops, I forgot that positive charge down here. We're almost there. This is a funky looking intermediate to draw. And this has a positive charge. So we're at our oxaphosphatane. And then in the next step, we said that this negative charge on this oxygen can clamp down, give us our 4-membered ring. Actually, let me move this hydrogen a little bit. Okay, and then the last step we said we have to dump these electrons down. We know that oxygen phosphorus double bond's really stable. And then we want to dump these bonds down. It honestly doesn't really matter which way you draw. You can draw it counterclockwise or clockwise. Yeah, it gives you the same product. Okay, and that's the full mechanism for a Wittig reaction. So now let's take a look at a problem that I could throw on an exam, like the one on Thursday. All right, practice. Box number 1 is starting material. Tricky, tricky. Step 1, we're going to treat it with triphenyl. Phosphine and then butyl lithium in step 2. So I'm kind of condensing this into one arrow. I'm asking you for the intermediate over here. This is 4 points. And then I want to know the intermediate that you need here, an additional 4 points, in order to give us this product. So we have to do a little bit of synthetic planning and then figure out what goes into each of these boxes. I'll give you guys a hint here. In this box we want our ylid, and down here we want our ketone or our aldehyde, right? So you first want to make your ylid, and then you want to add it into a ketone or aldehyde. Let's work backwards through this, right? So we know we want to form this carbon-carbon double bond. So the question we have now, I'm going to highlight this, is, do we want this green highlighted area to be our original ketone or aldehyde, or do we want kind of the blue portion, or sorry, pink portion of the ring to be our ketone or aldehyde?
Pink.
Or magenta, excuse me. Typically, you want your bulkiest substituent to be on your ketone or aldehyde, right? Because you need the less bulky substituent to act as your ylide. So if we think about this, let's fill it in. That means that the magenta ring must have been a ketone. That means the green portion must have been some sort of phosphorus ylide. So let's draw that in. We know it's 3 carbons long. Oops. Should be a CH3. I'll put H2 down here. And we've got a negative charge on this carbon because it's got a lone pair. All right, so that's our entire green portion with the 3 carbons. And now we've got to figure out what goes in that original box. What do you guys think? Yeah, propyl halide. Let's just do propyl bromide, right? So we know that we could have bromine with 3 carbons attached. Treat that with triphenylphosphine. Treat it with butyl lithium after that, and then throw in a ketone or aldehyde in order to form our new carbon-carbon double bond.
Would this work with any good leading group, like a OTS?
Yes, because it's SN2, you can pick any good leaving group. Yep. All right, does it make sense? It requires a lot of practice, so I really recommend going through the book when you're practicing the Wittig problems. They've got a whole list of good problems in there. All right, let's do our last reaction for the chapter. This is the Baeyer-Villiger oxidation.
Are they brothers?
No, it's typically 2 scientists that share credit, so they do the dash. I don't know the history of this reaction. I've got to look it up. In this reaction, you can also treat a ketone or an aldehyde with a peroxy acid. What's an example of a peroxy acid that we've used a lot? MCPBA, right? And when we do this, you get an inserted oxygen. It's a pretty unique reaction. So you can imagine if you start with an aldehyde, so one of those R groups is an H, what product will we get out of a Baeyer-Villiger oxidation? Yeah, carboxylic acid. And then if we start with a ketone, what new functional group will we get out? An ester. So it really depends on what we start with. But it's a nice way to functionalize a ketone or an aldehyde.
How do you know which side of oxygen to be inserted on the ketone?
We're going to get into that. Yeah, that's the next question. So let's do the mechanism. So if you guys didn't hear, she was asking, how do we know which side the oxygen gets inserted on? There's a special order of priorities. Okay, so let's just choose acetone, a nice simple example. And in this step, we're going to treat it with our peroxybenzoic acid. And it's a little bit weird. So in this reaction, this terminal oxygen on your peroxybenzoic acid will act as a nucleophile, tack into your ketone, and kick up electrons.
Excuse me, Professor.
Yep.
Why are you not doing the double arrow?
Because this is an equilibrium reaction. It's not a true one-way arrow. So,
Because you
Because in this case, oxygen's not a very good nucleophile. You could imagine, well, why doesn't this kick down and kick off that as a leaving group? And in fact, it does. This isn't a very favorable equilibrium. But let's see what can happen in this next step. In the next step, something bizarre happens. This oxygen will actually reach over and grab that proton. Traitor, yep. This oxygen still has a negative charge. Now this oxygen has the positive charge. And now the tricky part. In the next step, this entire group, so I'm going to label this as a CH3 group, this entire group will do an alkyl migration over to this oxygen. When this happens, this oxygen will dump electrons down and then dump electrons down. So this is called an alkyl shift. When this happens, the reaction is no longer in equilibrium. Oops, and sorry, this oxygen dumps its electrons down in this concerted process too. So when we look at this, we've got, whoops, the methyl group that now shifted over to that oxygen. And we end up with the double bonded oxygen here, there, and then we've got this R group. So you end up with a carboxylic acid byproduct. If we think about this alkyl shift or alkyl migration, there's an order of priorities. Hydrogens really like to shift, so they'll move over to that oxygen if you have a hydrogen coming off of that carbonyl carbon. The next best is tertiary carbons, so like a tert-butyl group is pretty good at migrating. Followed by secondary carbons, they're pretty good at migrating. Followed by a phenyl group. And then last but not least, you've got primary and you've got methyl. All of these were determined experimentally. So they tested these reactions and they saw which side of the ketone's more likely to migrate. In the case of aldehydes, the hydrogen really prefers to migrate, so you always form a carboxylic acid. But with ketones, you have to compare. Is one substituent tertiary? Is one secondary? Is one a phenyl group? Is one primary? Is one a methyl group? There's a lot of factors to consider. Let's do a couple of quick examples. Sorry, I know we're running short on time. And then tomorrow we'll just do all review. So let's do O3H here. What will our product look like? Does it matter which side we insert the oxygen on? No, it's symmetric, right? Is the ring going to change size at all? It'll get bigger, right? Because we're adding an atom into the ring. So right now we've got 5 carbon atoms making up the ring. However, if we insert an oxygen atom, it will make up the 6-membered side of the ring. And you can use this to form what's called a lactone. A lactone is basically just a cyclic ester. The other common example where this is used is with this. What will we get out? Yeah, carboxylic acid, and then in subsequent chapters we'll talk about how to functionalize carboxylic acids. One last really quick one. RCO3H. which side of the ketone will want to migrate onto the oxygen, the left side or the right side? Left side, right? It's secondary. Secondary is more likely to migrate over primary. So we know that oxygen will insert here, and you'll get that isopropyl group coming off of the oxygen. All right, I think that's where we're going to end today. The practice exam is online. Tomorrow we're just going to spend the whole day doing review.
On